What if our entire universe is inside a black hole? Tonight, we're going to explore one of the most mind-bending theories in cosmology. You've probably heard about black holes countless times, these cosmic monsters that devour everything, including light itself. But here's what most people don't realize. The mathematics describing our expanding universe are eerily similar to those describing a black hole's interior. By the end of this journey, you're going to understand why brilliant physicists think we might be living inside an unimaginably massive black hole, and why this terrifying possibility might explain everything we see. Before we dive in, if you enjoy these explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. This changed everything. Picture this. Imagine drawing an imaginary line around any massive object, like sketching a circle around a city on a map. This isn't a physical wall or barrier, it's purely mathematical, but it represents something profound. When anything crosses this special line, it can never return to tell what it saw on the other side. Think about what it takes to escape from where you're sitting right now. If you could throw a baseball hard enough, about 25,000 miles per hour, it would escape Earth's gravity completely and drift into space forever. That's Earth's escape velocity, the minimum speed needed to break free from our planet's gravitational grip. Now consider the Sun. Its escape velocity jumps to a staggering 384,000 miles per hour, more than 50 times greater than Earth's. You're starting to see the pattern, aren't you? As mass concentrates into smaller and smaller spaces, the escape velocity increases dramatically and predictably. But there's a universal speed limit in our cosmos. When that escape velocity reaches exactly 669,600,000 miles per hour, we arrive at an absolute physical boundary of nature itself. This is the speed of light, the universal speed limit that nothing in the cosmos can exceed. Here's where it gets interesting. In 1916, a German physicist named Karl Schwarzschild was solving Einstein's field equations in the trenches of World War I. He calculated that any mass compressed below a specific radius would create this extreme condition. The numbers are almost incomprehensible. If you could somehow compress our Sun into a sphere with a radius of just 1.9 miles, smaller than the distance between two neighborhoods, it would become a black hole. For Earth, that radius would be microscopic, just about 0.3 of an inch, smaller than a quarter. A black hole with the mass of Mount Everest would have a radius smaller than the width of a proton, invisible to the most powerful microscope ever conceived. But here's what's crucial to understand. The event horizon isn't a solid surface like Earth's crust. It's a mathematical boundary in space itself, the point where the curvature of space-time becomes so extreme that the very fabric of reality warps beyond recognition. Within this limit, all directions point inevitably toward the center, like one-way streets converging on a downtown intersection. For decades after Schwarzschild's calculations, physicists considered black holes nothing more than mathematical curiosities, bizarre solutions to equations that couldn't possibly exist in the real universe. They were theoretical anomalies, fascinating to contemplate but surely impossible in nature. Then the 1960s changed everything. Astronomers began detecting sources of X-rays that were extremely bright and variable, flickering and pulsing in ways that suggested something extraordinary was happening. In 1964, they discovered Cygnus X1, an invisible object with more than 10 times the mass of our Sun, orbiting a giant star. The matter being torn from that star and pulled toward the invisible companion was heating to millions of degrees, glowing so intensely it was detectable from thousands of light years away. But the real breakthrough came in 2019, when the Event Horizon Telescope captured something that had never been seen before. the first direct image of an actual event horizon. The supermassive black hole they photographed, designated M87 Gain, contains the mass of 5.4 billion suns concentrated into a region smaller than our solar system. Its event horizon has a radius of approximately 12.4 billion miles, about 3 times the orbit of Neptune. 3 years later, in 2022, they photographed Sagittarius A, the supermassive black hole at the center of our own Milky Way galaxy. These observations demonstrated beyond doubt that event horizons are real, measurable boundaries in the observable universe. The behavior of light around these boundaries confirms Einstein's predictions of general relativity with extraordinary precision. Near the event horizon of M87T, astronomers measured magnetic fields 26,000 times stronger than Earth's magnetic field. Jets of matter are ejected at speeds approaching the speed of light, confirming the extreme internal dynamics that Einstein's equations predicted. But perhaps most mind-bending of all is what happens to time itself. As you approach an event horizon, time progressively dilates, like clocks gradually slowing down. To an observer watching from a safe distance, anything falling toward a black hole would appear to freeze forever at the edge of the event horizon, its image red-shifted into invisibility. But for the unfortunate traveler crossing that boundary, time continues flowing normally until tidal forces become extreme. In smaller black holes, these forces would stretch and shred any object in a process astronomers call spaghettification. But supermassive black holes present a different scenario entirely. Their event horizons are so vast that you could cross the boundary without immediate destruction. The curvature is gentler, the tidal force is less intense at the moment of crossing. Here's something that might surprise you. Paradoxically, supermassive black holes have average densities lower than water at the moment you cross their event horizons. A stellar mass black hole might have densities trillions of times greater than an atomic nucleus, but as black holes become more massive, their average density actually decreases. The density drops with the square of the mass, creating a counterintuitive relationship between size and concentration. Yet all that mass remains contained within the event horizon, imprisoned by its own gravity. This is the fundamental nature of a black hole, a region of space-time with an absolute one-way boundary. Now let's shift our perspective to something much larger. The limits of the observable universe itself. Just as black holes have event horizons, our universe has its own kind of boundary. The observable universe possesses an absolute limit beyond which nothing can ever be seen or detected. This limit exists not because of technological limitations, but because of fundamental restrictions imposed by physics and geometry itself. The particle horizon marks the maximum distance from which light has had time to reach us since the Big Bang. Like a lighthouse beam cutting through ocean darkness, we can only see ships within the reach of light during the cosmic night. The finite age of the universe, 13.8 billion years, imposes a natural barrier on what can be observed. Due to the expansion of space itself, this horizon currently has a radius of approximately 29 billion light-years. But here's where things get truly interesting. If you could somehow compress all the matter in the observable universe into a single point, it would form a black hole. The Schwarzschild radius of that cosmic mass would be remarkably close to the radius of our current observable universe. This isn't a coincidence. It emerges naturally from the equations of general relativity applied to cosmology. The total mass of the observable universe is estimated at roughly 3.3 times 10 to the 53rd power-pounds of ordinary matter. Including dark matter, that value jumps to approximately 1.3 times 10 to the 54th pounds, distributed throughout the observable volume. When you apply Schwarzschild's formula to this total mass, You get a radius comparable to our cosmic horizon, but unlike a conventional black hole, there's no outside to our observable universe for comparison. The cosmic expansion means that regions currently distant were much closer together in the remote past. Objects beyond our cosmic event horizon are receding faster than light due to expansion itself. This doesn't violate special relativity. It's space itself that's expanding, carrying galaxies along like dots drawn on the surface of an inflating balloon. As the balloon inflates, distances between dots increase without the dots moving through the balloon's surface. The cosmic microwave background radiation, the afterglow of the Big Bang, comes from a time when the universe was only 380,000 years old. This radiation shows us a universe that was remarkably uniform in temperature, presenting what cosmologists call the horizon problem. How could regions of space that had never been in causal contact have identical temperatures? The leading explanation is cosmic inflation, a period when the universe expanded exponentially in the first tiny fraction of a second after the Big Bang. During inflation, causally connected regions were stretched beyond the limits of light-speed communication, solving both the horizon problem and explaining the observed flatness of space. In 1956, physicist Wolfgang Rindler defined an event horizon as the boundary beyond which events become permanently unobservable. This definition applies equally to black holes and to cosmology, creating profound mathematical parallels. The Friedmann equation for cosmology and the Schwarzschild metric for black holes share remarkably similar structures. Both describe spacetimes with causal horizons and singularities, where known physics breaks down completely. At the center of a black hole, density theoretically becomes infinite, creating what physicists call a spatial singularity. At the beginning of our universe, the Big Bang represents a temporal singularity of infinite density. The difference is that the Big Bang singularity lies in our past, while a black hole's singularity lies in the future of anything falling into it. In both cases, general relativity predicts that physical laws cease to function at these extreme points. But Stephen Hawking's work on black hole thermodynamics revealed something unexpected. Black holes aren't perfectly black. They emit radiation, slowly evaporating like steam escaping from a hot pot. Hawking demonstrated that a black hole's temperature is inversely proportional to its mass. Smaller black holes are hotter and evaporate more quickly, while massive ones remain cold for eons. A black hole with the mass of our Sun would take 10 to the 67th power years to evaporate completely, a time span so vast it defies human comprehension. Our observable universe also has a temperature, about 4.9 degrees Fahrenheit above absolute zero, from the cosmic microwave background radiation that's been stretched by expansion for 13.8 billion years. Remarkably, the calculated temperature for a black hole with the mass of our observable universe would be similar to this cosmic background radiation. This suggests deep thermodynamic connections between the properties of black holes and our universe. The internal geometry of a black hole permits local expansion of spacetime similar to cosmic expansion itself. Observers crossing an event horizon wouldn't detect anything special at that critical moment. The local laws of physics continue to operate normally even after crossing a black hole's one-way boundary. Similarly, inhabitants of our universe cannot directly detect whether they exist within some larger cosmic event horizon. General relativity allows regions inside black holes to contain expanding universes. In 1972, physicist Raj Pathria proposed the first cosmological model where our universe might be the interior of a black hole in some larger cosmos. He compared the external Schwarzschild metric with the internal Friedmann-Lemaitre-Robertson-Walker metric, suggesting that our Big Bang could be gravitational collapse viewed from the inside. The mathematics are elegantly consistent. What we experience as cosmic expansion could be the internal dynamics of space-time within an unimaginably massive black hole. The singularity we call the Big Bang would be the moment of formation of this cosmic black hole, while our expanding universe represents its internal evolution. This perspective transforms our understanding of cosmic boundaries and raises profound questions about the nature of reality itself. Are we prisoners in a cosmic structure from which no escape is possible? Or are we participants in something even more extraordinary than we've ever imagined? The answer may fundamentally reshape how we see our place in the cosmos. But for anyone crossing that boundary, time continues flowing normally until they encounter extreme tidal forces. In smaller black holes, these forces stretch and shred any object in a process astronomers call spaghettification. Picture yourself falling feet first toward a stellar mass black hole. The gravitational pull on your feet would be dramatically stronger than the pull on your head, a difference so extreme it would literally stretch you like taffy until you snapped apart. It's a gruesome end, but mercifully brief. Supermassive black holes present an entirely different scenario. They allow you to cross the event horizon without immediate destruction due to their much gentler curvature. The difference lies in distance. Larger horizons mean less intense tidal forces at the boundary itself. Here's the counterintuitive part. Paradoxically, supermassive black holes have average densities lower than water at the moment of crossing their event horizons. While stellar black holes possess densities trillions of times greater than an atomic nucleus, the average density decreases with the square of the mass, creating a completely counterintuitive relationship between size and concentration. Think about this for a moment. A black hole containing the mass of 5 billion suns might have an average density no greater than the air you're breathing right now. Yet all that mass remains contained within the event horizon, imprisoned by its own gravity. This is the fundamental nature of a black hole, a region of space-time with an absolute one-way boundary. Now let's consider a much larger perspective, the limits of the observable universe itself. Our observable universe possesses an absolute limit beyond which nothing can ever be seen or detected. This limit doesn't exist because of technological limitations, but because of fundamental restrictions imposed by physics and geometry themselves. The particle horizon marks the maximum distance from which light has had time to reach us since the Big Bang. Like a lighthouse beam cutting through ocean darkness, we can only see ships within the reach of light during the cosmic night. The finite age of our universe, 13.8 billion years, imposes a natural barrier on what can be observed. But due to the expansion of space itself, this horizon currently has a radius of approximately 29 trillion miles. That's vastly larger than the distance light could have traveled in 13.8 billion years, because space itself has been expanding while that ancient light was traveling toward us. Here's where things become truly extraordinary. If you could somehow compress all the matter in the observable universe into a single point, it would form a black hole. The Schwarzschild radius of that cosmic mass would be remarkably close to the radius of our current observable universe. This mathematical coincidence isn't accidental. It emerges naturally from Einstein's equations of general relativity applied to cosmology. The total mass of the observable universe is estimated at roughly 3.3 times 10 to the 53rd power-pounds of ordinary matter. When you include dark matter, that mysterious substance that outweighs normal matter by 5 to 1, that value jumps to approximately 1.3 times 10 to the 54th pounds distributed throughout the observable volume. Apply Schwarzschild's formula to this total mass, and you get a radius comparable to our cosmic horizon. But unlike a conventional black hole, there's no outside to our observable universe for comparison. The cosmic expansion means that regions currently separated by vast distances were much closer together in the remote past. The cosmic event horizon is different from the particle horizon. It marks regions we can never see, even given infinite time. Objects beyond this cosmic event horizon are receding faster than light due to the expansion of space itself. This recession velocity doesn't violate special relativity because it's space itself that's expanding, carrying galaxies along like dots drawn on the surface of an inflating balloon. As the balloon inflates, the distances between dots increase without the dots moving through the balloon's surface. This expansion means that our observable universe today contains regions that were causally disconnected in the past. Areas that could never have communicated with each other, even at the speed of light. This creates what cosmologists call the horizon problem. How can regions of space that have never been in causal contact have nearly identical temperatures? When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see temperature variations of only about 30 millionths of a degree Fahrenheit across the entire sky. The leading solution to this puzzle is cosmic inflation, a period when the universe expanded exponentially during the first tiny fraction of a second after the Big Bang. During inflation, causally connected regions were stretched beyond the limits of light-speed communication faster than you could blink. This rapid expansion would explain both the temperature uniformity and the observed flatness of space. But inflation creates its own horizon problem. Regions that were causally connected before inflation became permanently inaccessible afterward. In 1956, physicist Wolfgang Rindler defined an event horizon as the boundary beyond which events become permanently unobservable. This definition applies equally to black holes and to our universe, creating profound mathematical parallels. The Friedmann equation governing cosmic expansion and the Schwarzschild metric describing black holes share remarkably similar mathematical structures. Both describe spacetimes with causal horizons and singularities where known physics completely breaks down. At the center of a black hole, density theoretically becomes infinite, creating what physicists call a spatial singularity. At the beginning of our universe, the Big Bang represents a temporal singularity of infinite density. The crucial difference is that the Big Bang singularity lies in our past, while a black hole's singularity lies in the future of anything falling into it. In both cases, general relativity predicts that physical laws cease to function at these extreme points. But Stephen Hawking's work revealed something unexpected about black holes. They're not perfectly black. They emit radiation, slowly evaporating like steam escaping from a hot pot. Hawking demonstrated that a black hole's temperature is inversely proportional to its mass. Smaller black holes are actually hotter and evaporate more quickly, while massive ones remain cold for eons. A black hole with the mass of our Sun would take 10 to the 67th power years to evaporate completely, a time span so vast that the current age of the universe seems like an instant in comparison. By then, all the stars would have burned out, all the protons in the universe would have decayed, and space itself would be a cold, empty void, punctuated only by the occasional flash of a black hole, finally giving up its last breath of energy. Our observable universe also has a temperature, about 4.9 degrees Fahrenheit, above absolute zero, from the cosmic microwave background radiation that's been redshifted by expansion for 13.8 billion years. Remarkably, the calculated temperature for a black hole with the mass of our observable universe would be nearly identical to this cosmic background temperature. This suggests deep thermodynamic connections between black hole physics and cosmology. The internal geometry of a black hole actually permits local expansion of space-time, similar to the cosmic expansion we observe. Observers crossing an event horizon wouldn't detect anything special at that critical moment. The local laws of physics continue operating normally even after crossing a black hole's one-way boundary. Similarly, we inhabitants of this universe cannot directly detect whether we exist within some larger cosmic event horizon. General relativity allows regions inside black holes to contain expanding universes, and in 1972, physicist Raj Pathria proposed the first cosmological model where our universe might be the interior of a black hole in some incomprehensibly larger cosmos. He compared the external Schwarzschild metric with the internal Friedmann-Lemaitre-Robertson-Walker metric, and found something remarkable. The mathematics worked perfectly. Our Big Bang could be gravitational collapse viewed from the inside, while what we experience as cosmic expansion could be the internal dynamics of space-time within an unimaginably massive black hole. The singularity we call the Big Bang would be the moment of formation of this cosmic black hole, while our expanding universe represents its internal evolution over cosmic time. From the outside in the parent universe, our entire cosmic history, from the Big Bang to the formation of galaxies, stars, planets, and life itself, might represent just a few moments of gravitational collapse. But inside this cosmic event horizon, we experience billions of years of evolution, the formation of complex structures, and the emergence of consciousness capable of contemplating its own existence. The mathematics are not only consistent, they're elegantly beautiful in their symmetry. This perspective raises profound questions about cosmic boundaries and the ultimate nature of reality. If we are indeed inhabitants of a black hole's interior, then every astronomical observation, every measurement of cosmic expansion, every detection of distant galaxies would be measurements of the internal dynamics of this vast gravitational prison. The horizon problem in cosmology would find its natural explanation in the causal structure of black hole interiors. Cosmic inflation proposes that the primitive universe expanded exponentially in the first 10 to the negative 35th power seconds after the Big Bang. During inflation, causally connected regions were stretched beyond the limits of light-speed communication, faster than anything we can imagine. In that infinitesimal fraction of a second, so brief that calling it an instant seems like an eternity, space itself expanded by a factor of at least 10 to the 26th power. To put this in perspective, if a grain of sand expanded at the same rate, it would grow larger than our solar system. This ultra-rapid expansion would solve both the horizon problem and the observed flatness of space. Regions that appear disconnected today were once close enough to exchange information and reach thermal equilibrium. The temperature uniformity we see in the cosmic microwave background would be a natural consequence of this primordial connection. But inflation creates its own horizon dilemma. Regions that were causally connected before inflation became permanently inaccessible afterward, separated by distances so vast that even light traveling for the entire age of the universe couldn't bridge the gap. In 1956, physicist Wolfgang Rindler defined an event horizon as the boundary beyond which events become permanently unobservable. This definition applies equally to black holes and to our universe, creating profound mathematical parallels that can't be dismissed as mere coincidence. The Friedmann equation governing cosmology and the Schwarzschild metric describing black holes share remarkably similar structures. Both describe spacetimes with causal horizons and singularities where known physics completely breaks down. Both scenarios describe regions where density theoretically becomes infinite. At the center of a black hole, matter collapse creates what physicists call a spatial singularity. At the beginning of our universe, the Big Bang represents a temporal singularity of infinite density. The crucial difference is temporal direction. The Big Bang singularity lies in our past, while a black hole's singularity lies in the future of anything falling into it. In both cases, general relativity predicts that physical laws cease to function at these extreme points. Our mathematics simply break down when confronted with infinities. Hawking radiation suggests that black holes evaporate slowly, leaking energy like steam escaping from a hot pot. Stephen Hawking demonstrated that a black hole's temperature is inversely proportional to its mass, a relationship that defies common sense but emerges inevitably from quantum mechanics operating near event horizons. Smaller black holes are actually hotter and evaporate rapidly, while massive ones remain cold for eras. A black hole with our sun's mass would take 10 to the 67th power years to evaporate completely, a time span so incomprehensibly long that writing it out would require more digits than there are atoms in the observable universe. By the time such a black hole finally surrendered its last whisper of energy, the universe would be unrecognizably different. All stars would have burned out and died, all planets would have been consumed or frozen solid, and even protons themselves would have decayed into lighter particles. The universe would be a vast, cold emptiness, punctuated only by the occasional gamma-ray flash of an evaporating black hole. Our observable universe also possesses a temperature, about 4.9 degrees Fahrenheit above absolute zero, from the cosmic microwave background radiation that's been stretched by expansion for 13.8 billion years. This radiation is the thermal echo of the Big Bang, redshifted from blazing hot gamma rays to cool microwaves as space itself expanded. Remarkably, the calculated temperature for a hypothetical black hole containing the mass of our observable universe would be nearly identical to this cosmic background temperature. This can't be coincidental. It suggests deep thermodynamic connections between black hole physics and cosmology that we're only beginning to understand. The internal geometry of a black hole actually permits local expansion of spacetime, similar to the cosmic expansion we observe around us. Observers crossing an event horizon wouldn't detect anything special at that critical moment. Time would continue flowing normally, space would appear flat locally, and the laws of physics would continue operating exactly as expected. Similarly, we inhabitants of this universe cannot directly detect whether we exist within some larger cosmic event horizon. The laws of physics work the same way whether we're in a closed cosmic system or an open one. General relativity permits regions inside black holes to contain expanding universes, and this isn't just theoretical speculation. In 1972, physicist Raj Pathria proposed the first serious cosmological model where our universe might be the interior of a black hole in some incomprehensibly larger cosmos. He compared the external Schwarzschild metric, the mathematical description of spacetime around a black hole, with the internal Friedmann-Lemaitre-Robertson-Walker metric that describes our expanding universe. The mathematics aligned perfectly. Our Big Bang could represent gravitational collapse viewed from the inside, while what we experience as cosmic expansion could be the internal dynamics of spacetime within an unimaginably massive black hole. The singularity we call the Big Bang would be the moment of formation of this cosmic black hole. Lee Smolin expanded this idea in 1992, proposing that black holes generate daughter universes with physics slightly different from their parents. This process of cosmic natural selection would allow universes to evolve through generations of black hole formation. Universes with physics optimized for star formation would produce more black holes, generating more offspring. The fundamental constants of nature, the speed of light, the strength of gravity, the mass of elementary particles, might vary slightly from one generation to the next. Over billions of generations, this evolutionary process would favor universes capable of producing complex structures, stars, planets, and ultimately observers capable of contemplating their own existence. This cosmic natural selection would explain the apparent fine-tuning of physical constants in our universe. The cosmological constant seems precisely adjusted to allow galaxy formation. Slightly larger and cosmic expansion would prevent structure formation, slightly smaller, and the universe would collapse before stars could ignite. Similarly, if the strong nuclear force were just 5% weaker, hydrogen wouldn't fuse into helium and stars couldn't shine. If it were 5% stronger, all hydrogen would have fused into heavier elements during the first few minutes after the Big Bang, leaving no fuel for stellar fusion. The narrow range of values that permit complexity isn't accidental. It's the result of cosmic evolution, favoring universes that can produce observers. We wouldn't be here to contemplate these questions unless our universe possessed physics capable of generating the complexity that led to our existence. This cosmic selection principle resolves the fine-tuning problem without invoking intelligent design or infinite parallel universes. Our universe is special because we exist within it, and we exist within it because countless generations of cosmic evolution selected for the physical laws that make our existence possible. The diversity of daughter universes would create a vast, structured multiverse where each black hole becomes a cosmic egg, hatching a new reality. Some universes would expand too rapidly for structure formation, others would contract too quickly for stars to form. Only universes with nearly optimal parameters would develop sufficient complexity to generate observers and produce the next generation of cosmic offspring. This isn't science fiction, it's a testable hypothesis. If our universe is indeed the interior of a rotating black hole, it would inherit angular momentum from its parent. Recent observations from the James Webb Space Telescope have found intriguing evidence that might support this possibility: a systematic preference for clockwise rotation in distant galaxies. Statistically, only half the galaxies should rotate in each direction if the universe were truly isotropic, but analysis of more than 200 primitive galaxies shows a clear bias toward clockwise rotation. This asymmetry could indicate that our universe was born within a rotating black hole, inheriting a preferred axis that influences galaxy formation. All known black holes rotate, and this rotation would manifest as a privileged direction in the daughter universe. The rotation of the parent black hole would influence structure formation, creating the observed directional bias. This discovery challenges fundamental assumptions about cosmic isotropy and suggests our universe might indeed be the interior of a vast, rotating black hole in an incomprehensibly larger cosmos. In 2010, physicist Nikodem Poplawski developed a specific physical mechanism based on space-time torsion that could make this scenario not just possible, but inevitable. In Einstein-Cartan theory, torsion prevents singularities by causing a non-singular gravitational bounce. Instead of collapsing to infinite density, matter reaches an extreme but finite density and then expands rapidly. This bounce could explain the Big Bang as the internal expansion of a black hole in a larger universe. Think about what this means. Every time a massive star collapses to form a black hole in our universe, it might not create a point of infinite density. Instead, It could spawn an entirely new, expanding universe, a cosmic offspring that would be completely inaccessible to us, sealed away behind an event horizon that no signal can cross. The theory predicts that each black hole in our universe could contain a baby universe, invisible and unreachable from our perspective. The 100 billion black holes in our galaxy alone would represent 100 billion universes, each potentially teeming with stars, planets, and perhaps even life. Recent observations from the James Webb Space Telescope have found intriguing evidence for this possibility. An analysis of more than 200 primitive galaxies revealed a systematic rotational bias that shouldn't exist if our universe were truly uniform. Statistically, only half should rotate in each direction if the cosmos were isotropic. But the data shows a clear preference for clockwise rotation. This rotational asymmetry could indicate that our universe was born within a spinning black hole. All known black holes rotate, and this rotation would manifest as a preferred axis throughout the daughter universe. The parent black hole's angular momentum would influence galaxy formation, creating the directional bias we observe. Alternatively, our own Milky Way's rotation might contaminate distant observations in unexpected ways. But this would require a complete recalibration of distance measurements throughout the deep, observable universe, a prospect that would revolutionize our understanding of cosmic scales. Regardless of the ultimate explanation, this discovery challenges fundamental assumptions about cosmic isotropy. The cosmological principle, one of the bedrock assumptions of modern cosmology, states that the universe is homogeneous and isotropic on large scales. Violations of this fundamental symmetry would point toward new physics or unexpected cosmological structures. If our universe truly rotates, it would imply a non-zero total angular momentum from the moment of the Big Bang. The conservation of angular momentum would demand an explanation for the origin of this primordial rotation. A universe born within a rotating black hole would naturally inherit this angular motion. Future measurements of cosmic microwave background polarization could detect signs of universal rotation. The Planck satellite has already established rigorous limits on cosmic rotation, but recent discoveries justify renewed analysis with greater precision. Systematic gradients in temperature or polarization would reveal a preferred axis of rotation. Next-generation telescopes will map the rotation of distant galaxies with unprecedented accuracy. Ground-based observatories, like the extremely large telescope with its 165-foot mirror, will resolve individual stars in galaxies billions of light-years away. Space-based instruments will measure galaxy orientations across cosmic time, tracing the evolution of any universal rotation from the early universe to today. Confirmation of universal rotation would provide powerful evidence for black hole cosmology. But even without rotation, other characteristics connect black holes and cosmology in profoundly deep ways. The entropy of a black hole is proportional to the area of its horizon, not its interior volume. This relationship suggests that all information contained within a black hole is actually encoded on its two-dimensional surface. It's as if the three-dimensional interior is somehow projected from data stored on the boundary, a concept known as the holographic principle. Applied to our universe, this principle suggests that our three-dimensional reality could be a holographic projection of information encoded on a two-dimensional surface. That information would be stored on the cosmic horizon, the boundary of our observable universe. We would be, quite literally, holographic projections of data stored on the surface of our own cosmic boundary. Every thought you're thinking, every atom in your body, every star in the night sky, all of it might be the three-dimensional manifestation of information encoded on a distant two-dimensional surface. Quantum mechanics requires that information be conserved, even when matter falls into black holes. The information paradox questions how internal information can be preserved after a black hole evaporates through Hawking radiation. Proposed solutions include information leaking through the radiation or being stored on the event horizon itself. Similarly, our observable universe contains a finite amount of information limited by the particle horizon. Approximately 10 to the 120th power bits of information can be stored within the volume of our observable universe. A staggering number, but not infinite. This informational limitation suggests that reality is fundamentally discrete rather than continuous. Loop quantum gravity proposes that space-time itself is quantized at microscopic scales. At the Planck length, about 10 to the negative 33rd power inches, space might have a granular, discrete structure. This granularity could prevent true singularities from forming in both black holes and the Big Bang. Instead of infinite densities, there would be maximum finite densities where new physics emerges. The Planck density, roughly 10 to the 94th power-pounds per cubic inch, might represent a fundamental limit. Below this scale, classical concepts of space and time cease to have definite meaning. Quantum fluctuations of the vacuum dominate, creating a foaming, turbulent spacetime where geometry itself becomes uncertain. In this regime, there might be no clear distinction between the interior and exterior of black holes. Wormholes, Einstein-Rosen bridges, could connect event horizons to other regions of space-time, or even to other universes entirely. A black hole might be the entrance to a tunnel leading to a parallel cosmos or a distant region of our own universe. The corresponding exit would be a white hole, the time-reversed version of a black hole that expels matter instead of absorbing it. Our Big Bang could be interpreted as a white hole, gushing matter and energy into space-time. This perspective elegantly connects the creation of our universe with black hole physics. The interior of a black hole can expand exponentially, and this internal expansion would be invisible to outside observers due to the event horizon. The proper time within a black hole allows billions of years of evolution to occur in what seems like seconds to external observers. Stars, planets, and life could evolve completely within black holes without any external detection. Each supermassive black hole could harbor entire civilizations in internal bubble universes. The 100 billion known supermassive black holes represent 100 billion potential universes, each possibly containing its own web of galaxies, stars, and worlds. Our own Milky Way contains Sagittarius A, with the mass of 4 million suns. If our universe is the interior of a black hole, it would need to be incomparably more massive. The required mass would be trillions of times greater than the largest known black holes. This would demand formation in a parent universe with dramatically different scales and physics from our own. Alternatively, the formation mechanism for cosmic-scale black holes might differ radically from stellar collapse. Primordial black holes formed directly from density fluctuations in the early universe, requiring no stellar collapse. These objects could have any mass depending on initial conditions. If cosmic black holes exist, they could form through mechanisms impossible in smaller universes. The hierarchy of nested universes would create realities operating simultaneously on multiple scales. Universe children would inherit physical laws from universe parents with small random modifications. Fundamental constants like the speed of light or gravitational strength could vary slightly between generations. This variation would enable cosmic natural selection, favoring universes that produce more black holes. Universes with physics optimized for star formation would generate more descendants. The current cosmological constant appears fine-tuned to permit complex structure formation. Slightly different values would prevent galaxy formation or cause premature collapse. This fine-tuning could result from billions of generations of cosmic selection rather than incredible coincidence. Our universe would be the product of cosmic evolution, not a singular accident. The diversity of universe children would create a vast, structured multiverse where physical laws themselves evolve over cosmic generations. We would be literally holographic projections of data stored on the surface of our own horizon. Quantum mechanics demands that information be conserved, even when matter falls into black holes. This creates what physicists call the information paradox. How can information contained within a black hole be preserved after the black hole evaporates through Hawking radiation? If information truly vanishes when black holes disappear, it would violate one of the most fundamental principles of quantum mechanics. The paradox becomes even more perplexing when you consider the timescales involved. A black hole with the mass of our Sun would take 10 to the 67th power years to evaporate completely, a period so vast that the current age of our universe seems like a fleeting moment in comparison. During this incomprehensible span, the universe would transform beyond recognition. All stars would burn out, all planets would freeze or be consumed, and even protons themselves would decay into lighter particles. Proposed solutions to the information paradox include information slowly leaking out through Hawking radiation in incredibly subtle ways that we're only beginning to understand, or being stored permanently on the event horizon itself. But there's a parallel mystery in our own universe that might provide crucial insights into this puzzle. The observable universe contains only a finite amount of information, limited by the particle horizon that defines what we can ever hope to see. Approximately 10 to the 120th power bits of information can be stored within the volume of our observable universe. This number is astronomically large, vastly more information than exists in all the books, computers, and human minds on Earth combined, more than the number of atoms in billions of galaxies. Yet it's finite, not infinite. Think about what this means for the nature of reality itself. If information storage is fundamentally limited, then the universe might not be the smooth, continuous space-time that Einstein envisioned. Instead, it could be pixelated at the smallest scales, like a cosmic computer screen with incredibly tiny but finite resolution. This informational limitation suggests that reality is fundamentally discrete rather than continuous. Loop quantum gravity proposes that space-time itself is quantized at microscopic scales, chopped up into tiny, indivisible units that cannot be subdivided further. At the Planck length, about 10 to the negative 33rd power inches, space might have a granular, discrete structure that becomes apparent only at these unimaginably small scales. This granularity could prevent true singularities from forming in both black holes and the Big Bang. Instead of infinite densities that break our mathematics and violate physical intuition, there would be maximum finite densities where entirely new physics emerges. The Planck density, roughly 10 to the 94th power pounds per cubic inch, might represent a fundamental limit beyond which our current concepts of matter and energy simply don't apply. Below the Planck scale, classical concepts of space and time cease to have definite meaning. Quantum fluctuations of the vacuum become dominant, creating what physicists call quantum foam, a seething, turbulent space-time where geometry itself becomes uncertain and reality takes on an almost surreal character. In this regime, particles spontaneously appear and disappear, distances become fuzzy, and there might be no clear distinction between the interior and exterior of black holes. Wormholes, those theoretical Einstein-Rosen bridges that capture the imagination of science fiction writers, could connect event horizons to other regions of spacetime or even to entirely different universes. A black hole might be the entrance to a cosmic tunnel leading to a parallel universe or a distant region of our own cosmos, with the journey between them occurring through dimensions we cannot directly perceive. The corresponding exit would be a white hole, the time-reversed version of a black hole that expels matter instead of absorbing it. While black holes are gravitational sinks that pull everything inward, white holes would be gravitational fountains that push everything outward. No known white holes have been observed, but the mathematics of general relativity permits their existence. Our Big Bang could be interpreted as exactly such a white hole, gushing matter and energy into space-time from some unimaginable source beyond our cosmic horizon. This perspective elegantly connects the creation of our universe with black hole physics in ways that resolve several long-standing cosmological puzzles that have perplexed astronomers for decades. Consider the horizon problem that troubled cosmologists for years. How can regions of the cosmic microwave background that have never been in causal contact have nearly identical temperatures? If our Big Bang was actually a white hole connected to a black hole in a parent universe, these regions could have been thermally connected before being stretched apart by cosmic expansion. Theoretical models show that the interior of a black hole can expand exponentially, growing larger and larger over proper time measured by internal observers. This internal expansion would be completely invisible to outside observers due to the event horizon. No signal from within can ever reach the external universe to report what's happening inside the cosmic prison. The time dilation effects near black holes create a profound disconnect between internal and external perspectives. The proper time within a black hole allows billions of years of evolution to occur in what appears to external observers as mere seconds. Think about the implications. Entire cosmic epochs could unfold within black holes, while the outside universe barely advances. Stars could form from collapsing gas clouds, burn through their entire lifetimes, converting hydrogen to helium to carbon and beyond, expand into red giants, and explode as spectacular supernovae that illuminate their local regions of spacetime. Planets could cool from molten rock, develop stable atmospheres, and become suitable for life. Oceans could form, continents could drift, and the complex chemistry of life could emerge from simple organic molecules. Life itself could evolve from single-celled organisms to complex multicellular creatures, developing nervous systems, consciousness, and intelligence. Entire civilizations could rise and fall, discover fire, invent writing, develop science and technology, explore their local cosmic environment, and perhaps even discover that they live within a black hole, all completely undetectable from the parent universe outside. Each supermassive black hole could harbor entire civilizations in internal bubble universes that experience billions of years of history, while external observers see only the brief moment of gravitational collapse. The 100 billion known supermassive black holes in the observable universe would represent 100 billion potential universes, each possibly containing its own cosmic web of galaxies, stars, and worlds. Some of these internal universes might develop differently than ours. Perhaps they would have stronger or weaker fundamental forces, different particle masses, or alternative ratios of matter to energy. Some might expand more rapidly, preventing galaxy formation. Others might expand more slowly, leading to early gravitational collapse. Only a fraction would develop conditions suitable for complex structure formation and the emergence of life. Our own Milky Way contains Sagittarius A, a supermassive black hole with the mass of 4 million suns concentrated into a region smaller than Mercury's orbit. But if our universe is truly the interior of a black hole, it would need to be incomparably more massive. The required mass would be trillions of times greater than the largest known black holes, a scale so vast it defies human comprehension. This would demand formation in a parent universe with dramatically different scales and physics from our own. Imagine a cosmos where galaxies are as common as stars are in our universe, where superclusters of galaxies merge as routinely as binary stars do here, where the fundamental forces operate on entirely different energy scales. In such a reality, the formation of cosmic-scale black holes might be as routine as stellar collapses in our cosmos. The parent universe would need to have physical constants and evolutionary history that permitted the formation of structures massive enough to collapse into universe-generating black holes. Perhaps dark matter plays a different role there, or perhaps the cosmological constant has a different value that allows much larger structures to form before cosmic expansion tears them apart. Alternatively, the formation mechanism for cosmic-scale black holes might differ radically from anything we observe in our universe. Primordial black holes formed directly from density fluctuations in the early universe, requiring no stellar collapse whatsoever. These objects could theoretically have any mass, depending entirely on the initial conditions and the amplitude of density fluctuations when they formed. If cosmic black holes exist, they could form through mechanisms that are simply impossible in smaller universes like ours. Perhaps they require specific conditions that only exist in universe parents of enormous scale, particular ratios of different types of matter, specific patterns of cosmic expansion, or exotic physics that emerges only at scales vastly larger than anything we can observe. The hierarchy of nested universes would create realities operating simultaneously on multiple scales, like Russian dolls of cosmic complexity. Universe children would inherit physical laws from their universe parents, but with small, random modifications, like genetic mutations in biological evolution, but applied to the fundamental constants of nature itself. Fundamental constants like the speed of light, the strength of gravity, the mass of elementary particles, or the cosmological constant could vary slightly between cosmic generations. Most variations would be detrimental, producing universes incapable of forming complex structures. But occasionally, random changes would improve a universe's ability to generate black holes and produce cosmic offspring. This variation would enable cosmic natural selection on an unimaginable scale. Universes with physics optimized for star formation would generate more black holes, producing more descendants that carry forward their successful physical laws. Those with unsuitable physics would be evolutionary dead ends, producing few or no offspring to carry their characteristics into the next cosmic generation. The current cosmological constant in our universe appears remarkably fine-tuned to permit complex structure formation. If it were slightly larger, cosmic expansion would accelerate so rapidly that galaxies could never condense from the primordial gas clouds left over from the Big Bang. If it were slightly smaller, the universe would collapse in a big crunch before stars had time to ignite nuclear fusion and forge the heavy elements necessary for planets and life. Similarly, if the strong nuclear force were just 5% weaker, hydrogen nuclei wouldn't bind together effectively and stars couldn't sustain the fusion reactions that make them shine. If it were 5% stronger, all hydrogen would have fused into heavier elements during the first few minutes after the Big Bang, leaving no stellar fuel for the billions of years of cosmic evolution that followed. This remarkable fine-tuning could result from billions of generations of cosmic selection, rather than incredible coincidence or divine intervention. Our universe would be the product of cosmic evolution, a descendant of countless previous generations that gradually optimized the physical laws for complexity and structure formation through the blind but effective process of natural selection. But this raises an even more profound question that strikes at the heart of our existence. If we are indeed inhabitants of a black hole's interior, what does this mean for our ultimate fate and our place in the cosmic hierarchy? Alternatively, the formation mechanism for cosmic-scale black holes could differ radically from the stellar collapse we observe in our universe. Primordial black holes formed directly from density fluctuations in the early universe, requiring no stellar collapse whatsoever. In the first fraction of a second after the Big Bang, when the universe was incredibly dense and hot, regions with slightly higher density could collapse directly into black holes without ever forming stars first. These objects don't require the complex stellar evolution that produces the black holes we observe today. These primordial objects could theoretically have any mass, depending entirely on the initial conditions and the amplitude of density fluctuations when they formed. Some might be microscopic, smaller than atomic nuclei, yet containing the mass of mountains. Others could be astronomical in scale, dwarfing even the supermassive black holes at the centers of galaxies. If cosmic black holes exist, they could form through mechanisms that are simply inaccessible in smaller universes like ours. Perhaps they require specific conditions that only exist in universe parents of enormous scale, particular ratios of different types of exotic matter, specific patterns of cosmic expansion that we've never encountered, or physics that emerges only at scales vastly larger than anything we can observe. The hierarchy of nested universes would create realities operating simultaneously on multiple scales, like an infinite series of Russian dolls, each containing entire cosmos within cosmos. Universe children would inherit physical laws from their universe parents, but with small, random modifications that accumulate over cosmic generations. Think about what this inheritance process might look like. Fundamental constants like the speed of light, the strength of gravity, the mass of elementary particles, or the cosmological constant could vary slightly between cosmic generations. Most of these variations would be detrimental, producing universes incapable of forming the complex structures necessary for star formation and black hole creation. But occasionally, random changes would improve a universe's ability to generate black holes and produce cosmic offspring. A slightly stronger, strong nuclear force might make stars burn more efficiently, producing more heavy elements and more stellar remnants. A marginally different cosmological constant might allow larger structures to form before cosmic expansion tears them apart. This variation would enable cosmic natural selection on an unimaginable scale that dwarfs biological evolution on Earth. Universes with physics optimized for star formation would generate more black holes, producing more descendants that carry forward their successful physical laws into the next cosmic generation. Those with unsuitable physics would be evolutionary dead ends, producing few or no offspring to propagate their characteristics. The diversity of universe children would create a vast, structured multiverse where some universes expand too rapidly for structure formation. Their matter scattered so quickly that gravity never gets a chance to pull gas clouds together into stars. Others would contract too rapidly, collapsing in a big crunch before nuclear fusion could ignite in the first generation of protostars. Some universe children might have physics so exotic that familiar matter cannot exist. Perhaps the electromagnetic force is too weak to hold atoms together, or the strong nuclear force is too feeble to bind protons and neutrons into stable nuclei. In such universes, only energy fields and elementary particles would persist, with no possibility of complex chemistry or structure formation. Only universes with nearly optimal parameters would develop sufficient complexity to generate observers capable of contemplating their own existence and produce the next generation of cosmic offspring. We exist precisely because our cosmic ancestors possessed physics adequate for generating the complexity that led to our emergence. This cosmic selection principle resolves the fine-tuning problem without invoking either intelligent design or infinite parallel universes containing every possible combination of physical laws. The apparent fine-tuning of our universe's constants isn't evidence of supernatural intervention. It's the inevitable result of billions of generations of cosmic evolution favoring universes capable of producing observers. But the testability of this theory requires specific observational predictions that can be verified or falsified through astronomical observations. Universal rotation would be a clear signature of origin within a rotating black hole. If our universe inherited angular momentum from its parent, we should detect systematic rotational patterns in the cosmic microwave background or in the large-scale distribution of galaxies. Slightly positive spatial curvature would indicate the closed geometry expected from the interior of a black hole, rather than the flat or open geometry of an infinite universe. Current observations suggest our universe is remarkably flat, but future precision measurements might detect the subtle curvature predicted by black hole cosmology. Subtle deviations in the cosmic microwave background radiation could reveal special boundary conditions that differ from standard Big Bang predictions. The temperature and polarization patterns in this primordial light might contain signatures of the gravitational collapse that created our cosmic black hole. Violations of Lorentz invariance at extreme scales would point toward the discrete structure underlying spacetime at the Planck scale. If spacetime is truly quantized into tiny pixels, then particles with extremely high energies might experience slightly different physics than current theories predict. Non-local correlations in matter distribution would reflect non-trivial spacetime topology, the idea that our universe might be connected to other regions through wormholes or higher dimensional structures. Galaxy surveys might reveal patterns that can't be explained by simple gravitational clustering from random initial conditions. The polarization of light from distant quasars could show effects of space-time torsion, the twisting of the fabric of space-time itself that some theories predict occurs in black hole interiors. As light travels billions of years through twisted space-time, its polarization vector might rotate in characteristic ways. Precise measurements of fundamental constants over cosmic time could detect the predicted drift as our universe evolves within its black hole parent. If the fine structure constant or gravitational constant varies slightly as the internal space-time geometry evolves, we might detect these changes by comparing the physics of distant galaxies with local laboratory measurements. Observations of ultra-high-energy cosmic rays would reveal cutoffs at the Planck scale, where quantum gravity effects become important. If space-time truly has a discrete structure, then particles with energies approaching the Planck energy should behave differently than classical physics predicts. Detection of primordial gravitational waves would confirm phase transitions in the early universe that might be characteristic of black hole interior evolution. These waves, generated in the first moments after our cosmic birth, could carry information about the conditions during the formation of our parent black hole. Mapping cosmic voids, the vast empty regions between galaxy filaments, would show patterns specific to black hole cosmology models. The size, shape, and distribution of these voids might differ subtly from what standard cosmology predicts, revealing the influence of our cosmic boundary conditions. The absence of magnetic monopoles would be naturally explained by black hole topology. Standard cosmology struggles to explain why these exotic particles, predicted by many theories, have never been observed. Black hole interiors might have topological properties that prevent monopole formation. Distributions of primordial black hole masses would follow specific predictions from the theory. If every black hole in our universe contains a daughter universe, then the mass spectrum of black holes should reflect the evolutionary history of cosmic natural selection. Measurements of dark energy's evolution would show temporal patterns characteristic of internal black hole geometries. The accelerating expansion we observe might not be driven by a cosmological constant, but by the evolving geometry of spacetime within our cosmic parent. Correlations in quantum vacuum fluctuations would reveal the holographic structure underlying reality. If our three-dimensional universe is truly a projection from information stored on a two-dimensional boundary, then careful measurements of quantum fields might detect signatures of this holographic encoding. Laboratory experiments in quantum gravity might detect torsion effects that confirm we live in a black hole interior. Precision measurements of gravitational interactions at microscopic scales could reveal the space-time twisting that Einstein-Cartan theory predicts prevents true singularities. Advanced computer simulations would test the stability of bubble universes within black hole interiors. These models could explore whether internal expansion can continue indefinitely or whether some configurations lead to internal collapse or other exotic phenomena. Studies of extremely rotating black holes would reveal the dynamics of daughter universe formation. By observing matter falling into rotating black holes and measuring their internal properties through gravitational waves, we might understand how new universes are born. Statistical analyses of cosmological parameters would identify evidence of natural selection in the values of fundamental constants. If cosmic evolution has been optimizing physics for black hole production over many generations, the pattern of these constants should show signatures of this evolutionary process. Comparisons between different regions of the observable universe would show subtle gradients or variations that reveal our position within a larger structure. If we truly inhabit a black hole interior, different regions of our observable universe might show slight variations reflecting our cosmic boundary conditions. Measurements of the Hubble constant at multiple scales would reveal deviations from perfect homogeneity. The expansion rate might vary slightly in different directions or at different distances, reflecting the curved space-time geometry of our black hole interior. If confirmed through these diverse observational tests, this theory would revolutionize our understanding of reality more completely than any scientific discovery in human history. We would discover that our universe is not a closed, unique system, but rather a node in an incomprehensibly vast cosmic network that extends far beyond anything we had ever imagined possible. The absence of magnetic monopolies would be naturally explained by black hole topology, resolving one of the persistent mysteries that has puzzled physicists for decades. Standard cosmology struggles to explain why these exotic particles, predicted by many fundamental theories of physics, have never been observed despite intensive searches. In most models of the early universe, magnetic monopoles should have been produced in abundance during phase transitions in the first moments after the Big Bang. Their complete absence suggests that our universe has topological properties that prevent monopole formation, exactly what we might expect from the interior of a black hole. Distributions of primordial black hole masses would follow specific predictions from cosmic evolution theory. If every black hole in our universe contains a daughter universe, then the mass spectrum of these objects should reflect billions of generations of cosmic natural selection. We should see an overabundance of black holes with masses that optimize star formation and cosmic structure development. The most successful universe parents would be those that produce the most black hole offspring, and their mass distributions would dominate the cosmic gene pool. Current observations show intriguing patterns in black hole masses. distinct peaks at certain values and apparent gaps at others that might represent the evolutionary optimization of cosmic reproduction. Measurements of dark energy's evolution would show temporal patterns characteristic of internal black hole geometries. The accelerating expansion we observe might not be driven by a simple cosmological constant, but by the evolving space-time geometry within our cosmic parent. As our universe ages within its black hole prison, the internal curvature might change in ways that affect the apparent expansion rate. This could explain why dark energy seems to have a density remarkably close to the critical value that allows structure formation. In a naturally evolving black hole interior, the expansion rate would automatically adjust to maintain conditions favorable for complexity. Another signature of cosmic natural selection operating on incomprehensible scales. Correlations in quantum vacuum fluctuations would reveal the holographic structure underlying reality itself. If our three-dimensional universe is truly a projection from information stored on a two-dimensional boundary, then careful measurements of quantum fields should detect signatures of this holographic encoding. The vacuum isn't truly empty. It seethes with virtual particles that appear and disappear on timescales so brief they seem to violate energy conservation. But these quantum fluctuations might show subtle patterns that reflect the information processing occurring on our cosmic horizon. Laboratory experiments in quantum gravity could detect torsion effects that confirm we live within a black hole interior. Einstein-Cartan theory predicts that spacetime has not just curvature, but also torsion, a twisting that prevents true singularities from forming. Precision measurements of gravitational interactions at microscopic scales might reveal this space-time twisting. Advanced gravitational wave detectors, sensitive to distortions smaller than 1/10,000th the width of a proton, could potentially detect the signatures of torsion in the fabric of space-time itself. Advanced computer simulations would test the stability of bubble universes within black hole interiors. These models could explore whether internal expansion can continue indefinitely or whether some configurations lead to internal collapse, oscillation, or other exotic phenomena. The mathematics are incredibly complex. Simulating even a small patch of quantum spacetime requires computational resources that push the limits of current technology. But these simulations might reveal crucial insights about our ultimate fate. Do universe bubbles within black holes expand forever, eventually becoming cold and empty? Do they oscillate between expansion and contraction in eternal cycles? Or do they eventually reach some equilibrium state where expansion balances gravitational attraction? Studies of extremely rotating black holes would reveal the dynamics of daughter universe formation. When black holes spin at nearly the maximum possible rate, just shy of the point where they would tear themselves apart, their internal geometry becomes incredibly complex. The dragging of spacetime creates regions where the normal relationships between space and time break down. By observing matter falling into these extreme objects and measuring their properties through gravitational waves, we might understand how new universes are born. The birth process might require specific conditions, particular spin rates, mass ranges, or environmental factors that determine whether a collapsing star produces a simple black hole or a universe-generating cosmic egg. Statistical analyses of cosmological parameters would identify evidence of natural selection in the values of fundamental constants. If cosmic evolution has been optimizing physics for black hole production over many generations, the pattern of these constants should show signatures of this evolutionary process. The relationships between different constants should reflect not random chance, but billions of years of selection pressure favoring successful cosmic reproduction. We might find that seemingly unrelated constants are actually fine-tuned, relative to each other in ways that maximize the universe's ability to form stars and black holes. The mass of the proton, the strength of the electromagnetic force, and the rate of cosmic expansion might all be perfectly calibrated to work together in producing the maximum number of cosmic offspring. Comparisons between different regions of our observable universe would show subtle gradients or variations that reveal our position within a larger structure. If we truly inhabit a black hole interior, different regions of our cosmic bubble might show slight variations in fundamental constants or expansion rates, reflecting our location relative to the cosmic boundary. These variations would be incredibly subtle, perhaps detectable only through precision measurements of distant supernovae, gravitational lensing effects, or the cosmic microwave background radiation. But their discovery would provide direct evidence of our cosmic imprisonment and reveal details about the structure of our parent black hole. Measurements of the Hubble constant at multiple scales would reveal deviations from perfect homogeneity that standard cosmology cannot explain. The expansion rate might vary slightly in different directions or at different distances, reflecting the curved space-time geometry of our black hole interior. Current observations already show some puzzling inconsistencies in Hubble constant measurements, the so-called Hubble tension that might be early hints of these geometric effects. If confirmed through these diverse observational tests, this theory would revolutionize our understanding of reality more completely than any scientific discovery in human history. The implications would be so profound that they would fundamentally alter not just cosmology and physics, but philosophy, religion, and our basic conception of existence itself. Our position in the cosmos would be fundamentally different from what we have always imagined. We would not inhabit the central region of creation, emerging from a singular Big Bang in an open, infinite universe. Instead, we would be residents of the interior of a structure within a universe incomparably larger than anything we had ever conceived. The exterior would be literally inaccessible, protected by an absolute event horizon that no signal, no matter, no information can ever cross from the inside out. Any attempt to escape our cosmic prison would lead us inevitably toward the center, not outward toward freedom. This isn't a limitation of technology or energy. It's a fundamental property of the space-time geometry we inhabit. There exists no outside in the conventional sense for inhabitants of a black hole interior. All spatial directions eventually converge toward the central singularity. Even if we could travel at the speed of light, the ultimate speed limit of the universe, we would never reach the boundary that separates us from the parent cosmos. The expansion of internal space-time could indefinitely outpace any attempt at escape. As we moved toward what we thought was the edge of our prison, space itself would expand faster than we could traverse it, keeping the boundary forever beyond our reach. We would be cosmic prisoners in a jail from which no liberation is possible. But this prison would be indistinguishable from a free universe for internal observers like ourselves. The local physics would remain valid, permitting the full richness of existence, the formation of stars and planets, the emergence of life, the evolution of consciousness, and the pursuit of scientific knowledge. We could develop the most advanced technology imaginable without ever suspecting our true condition. Entire civilizations could flourish and disappear over cosmic time without ever gaining knowledge of the truth. They might explore their local galactic neighborhood, colonize nearby star systems, and even venture to distant galaxies, all while remaining completely unaware that their entire observable universe is contained within a structure in an incomparably larger reality. The search for cosmic understanding would become an infinitely ironic endeavor. Every astronomical observation, every measurement of cosmic expansion, every detection of gravitational waves would be the study of our own cosmic cage. We would be studying structures that are mere reflections of a reality forever beyond our reach. Each discovery about black holes would be a discovery about the nature of our own cosmos. Every measurement of event horizons would be contemplation of our own cosmic boundary. Studies of space-time curvature would be medical examinations of our existential condition, revealing the architecture of our imprisonment without offering any hope of escape. The search for extraterrestrial life would be a search for other consciousnesses imprisoned alongside us, not for civilizations in an open cosmos. Every radio telescope scanning the skies, every analysis of potentially habitable exoplanets, every attempt to detect biosignatures in distant atmospheres would be looking for fellow prisoners rather than free cosmic citizens. The profound loneliness that drives our search for cosmic companions would take on an entirely different meaning. We wouldn't be seeking contact across the vastness of space, but rather trying to find other minds trapped within the same cosmic cell. Space exploration would be exploration of our cosmic prison, not of a free universe. Every rocket we launch, every probe we send to distant worlds, every ambitious plan to reach other star systems would be movements within our gravitational jail. The most distant galaxies visible through our most powerful telescopes would still be regions of the same confined structure. ICT, the search for extraterrestrial intelligence, would be looking for signals from other prisoners, not from civilizations in an open cosmos. Those radio messages we beam toward distant stars, hoping for replies that might arrive centuries or millennia later, would be notes passed between cells in a vast cosmic penitentiary. Interstellar travel, that ultimate dream of human expansion, would lead only to other regions of the same cosmic cell. Even if we develop technologies that could propel us at significant fractions of light speed, even if we could somehow overcome the immense challenges of crossing the 4.2 light-years to Proxima Centauri or the 25,000 light-years to the galactic center, we would still be moving within our prison. Colonization of exoplanets would be redistribution within the same gravitational confinement. Those Earth-like worlds we discover orbiting distant stars, those potentially habitable zones where liquid water might exist and life might flourish, would all be rooms in the same cosmic structure. We could spread across thousands of worlds and still never approach true freedom. Even expansion throughout our entire galaxy, colonizing all 200 billion stars, terraforming countless worlds, building civilizations that span the full 100,000 light-year diameter of the Milky Way, would not represent real escape. The Andromeda galaxy, racing toward us at 250,000 miles per hour and destined to merge with our galaxy in 4 billion years, would simply be another wing of the same vast prison. Knowledge of this truth would transform human perspectives more profoundly than any discovery in our species' history. Dreams of cosmic transcendence, those aspirations that drive our greatest scientific endeavors and fuel our most ambitious space exploration programs, would be recognized as fundamentally impossible. There exists no accessible beyond, only more distant regions of the same confined structure. The infinite cosmos that has inspired poets, philosophers, and scientists for millennia would reveal itself as an illusion created by the extreme curvature of spacetime. What appears to extend endlessly in all directions would actually curve back on itself in ways our three-dimensional minds struggle to comprehend. Straight lines would eventually return to their point of origin in this closed geometry, just as a line drawn on the surface of a sphere will curve around and meet itself if extended far enough. Travelers moving in any direction for sufficient time would find themselves returning to their starting point, having circumnavigated the finite but boundless interior of our cosmic prison. The universe would be finite but unlimited, like the surface of a sphere existing in higher dimensions that we cannot directly perceive. Cosmic explorers would be like ants walking on the surface of a soccer ball. They could travel indefinitely without ever encountering an edge, but they would never escape the surface that confines them. The crucial difference is that our three-dimensional space would be the surface of a four-dimensional structure that we cannot visualize or access. This hyperbolic geometry would create the illusion of infinite expansion within a fundamentally finite space. The cosmic horizon we observe, that boundary beyond which we cannot see due to the finite age and expansion of the universe, would be an artifact of our position within this interior structure. Different observers located elsewhere in our cosmic prison would see slightly different horizons, but all would be internal boundaries rather than edges of an infinite cosmos. The cosmic microwave background radiation, that faint afterglow of the Big Bang that fills the entire sky, would be the echo of conditions during our internal creation rather than the remnant of a universe-wide explosion. The primordial density fluctuations that we observe in this background radiation, those tiny variations in temperature that eventually grew into galaxies and large-scale cosmic structures, would reflect the specific conditions of the gravitational collapse that generated our cosmic black hole. Every pattern we see in the cosmic web, the filaments of galaxies separated by vast voids, would be determined by the initial conditions of our cosmic formation. Big Bang nucleosynthesis, that remarkable process in the first few minutes of cosmic history when protons and neutrons combined to form the first atomic nuclei, would be a chemical process during our internal formation rather than the primordial creation of matter itself. The precise ratios of hydrogen, helium, and lithium that we observe throughout the universe would reflect the specific physics operating within our black hole interior. Recombination, that critical moment roughly 380,000 years after the Big Bang, when electrons first combined with nuclei to form neutral atoms, would be a specific phase transition in our internal development. This event made the universe transparent for the first time, allowing light to travel freely and creating the cosmic microwave background we observe today. Each cosmic era would represent a stage in the internal development of our parent black hole. The inflationary epoch, that period of exponential expansion in the first tiny fraction of a second, would be the period of extremely rapid expansion immediately following the gravitational bounce that prevented true singularity formation. The radiation era, when the universe was dominated by photons and other massless particles, would correspond to the cooling phase after maximum density was reached. During this period, the internal spacetime would be filled with intense electromagnetic radiation, gradually cooling as expansion continued. The matter era, when gravitational attraction began to overcome the outward pressure of radiation and allowed the first structures to condense, would mark the formation of complex gravitational structures within our cosmic interior. This transition, occurring roughly 50,000 years after our cosmic birth, would represent the moment when our internal universe became capable of forming the stars and galaxies we observe today. The current era of dark energy dominance, characterized by accelerating expansion that began roughly 5 billion years ago, would represent accelerated expansion within the curved geometry of our black hole interior. This acceleration might be driven not by some mysterious cosmic constant, but by the evolving internal geometry as our cosmic prison ages. The ultimate fate of our universe would be determined by the long-term internal dynamics of black hole evolution rather than by the simple extrapolation of current expansion trends. The Big Rip, a scenario where accelerating expansion eventually tears apart all gravitationally bound structures, would be one possible outcome for internal evolution. Alternatively, we might face a big crunch, where expansion eventually reverses and everything collapses back toward the central singularity. Or we might experience heat death, where expansion continues indefinitely, but all energy gradually dissipates into a cold, empty void, punctuated only by the occasional decay of fundamental particles. Each of these scenarios would represent different aspects of black hole physics operating on cosmic scales. Each possibility would represent different aspects of black hole physics operating at scales we can barely comprehend. Accelerated expansion could continue indefinitely in some internal geometries, carrying galaxies ever farther apart until they disappear beyond each other's cosmic horizons. In this scenario, our universe would grow cold and empty over trillions upon trillions of years, with individual stars burning out one by one until only black holes remain, slowly evaporating through Hawking radiation into a sea of elementary particles. Alternatively, expansion could eventually decelerate and reverse into contraction, bringing everything back together in a cosmic implosion. A recontracting universe would lead everything back toward the central singularity in a mirror image of the Big Bang, what cosmologists call the Big Crunch. Galaxies would merge, stars would be torn from their orbits, and eventually all matter would be compressed back into the incredibly dense state from which our universe emerged. This would create a closed cycle, expansion followed by contraction in perpetual oscillation. Cyclic universes would be like the heartbeats of cosmic black holes, rhythmically expanding and contracting over cosmic time. Each cycle could last trillions of years, as measured by internal proper time, longer than our current universe has existed by factors of thousands. But here's where the perspective becomes truly mind-bending. Each complete cycle would represent only instants in the time frame of the external parent universe. Extreme relativity distorts temporal perceptions between these vastly different scales. Our entire cosmic history, from the Big Bang through galaxy formation, stellar evolution, planetary development, and the emergence of life and consciousness, would be a microscopic fraction of a second as measured by external observers. Think about what this means. Civilizations could rise and fall, entire species could evolve and go extinct. Technologies could advance from stone tools to interstellar travel, all in what amounts to the blink of an eye from the perspective of the larger cosmos. Our universe's complete timeline, stretching back 13.8 billion years to the Big Bang and potentially extending trillions of years into the future, would flash by like a single frame in a cosmic movie. The very notion of time becomes relative and dependent on perspective in ways that challenge our most basic assumptions about reality. There exists no absolute time, only the proper time experienced by each observer within their own reference frame. Our experience of temporal flow is valid only within our imprisoned reference frame. Time in the exterior parent universe flows on scales incomparably larger than anything we can imagine. Events that we consider eternal, the lifespan of stars, the slow drift of continents, the evolution of species over millions of years, are merely transitory fluctuations from the larger perspective. The formation of our entire solar system, that gradual process of gravitational collapse and accretion that took millions of years to create the sun, planets, and moons we know today, would be essentially instantaneous from an external viewpoint. The 4.5 billion year history of Earth, from its molten birth through the emergence of life, the development of photosynthesis, the explosion of multicellular complexity, and the eventual evolution of human consciousness, would occupy an infinitesimal fraction of a second. All of recorded human history, from the first agricultural settlements 10,000 years ago through the rise and fall of civilizations, the development of writing, mathematics and science, the Industrial Revolution, the space age, and our current technological civilization, would be briefer than the vibration of a single atom in the external universe. Our greatest scientific achievements would be imperceptible from the outside. The discovery of fire, the invention of the wheel, the development of astronomy and physics, the splitting of the atom, the sequencing of DNA, the detection of gravitational waves, all of these milestones in human understanding would occur and pass unnoticed by any external observers. The discovery of this very truth, the realization that we exist within a black hole interior, would be simultaneous with its complete irrelevance to the external cosmos. No signal announcing our breakthrough could ever escape our event horizon to inform the parent universe of our existence or our understanding. Paradoxically, this revelation would be infinitely more significant from our internal perspective than it could ever be externally. Understanding our true condition wouldn't alter the fundamental reality of our cosmic imprisonment, but it would radically transform the meaning of existence and purpose for conscious beings like ourselves. If we cannot transcend our boundaries physically, we might still transcend them conceptually through the power of understanding itself. Knowledge of the truth would represent a form of absolute mental freedom that no physical confinement could diminish. Complete comprehension of our reality would substitute for the impossible physical escape. This cosmic wisdom would compensate for our gravitational imprisonment in ways that purely physical transcendence never could. While our bodies and technologies remain forever bounded by the event horizon, our minds could grasp the full scope of reality across scales that dwarf our physical existence. The search for knowledge would gain maximum existential urgency under these circumstances. Every scientific discovery would become an act of defiance against cosmic limitation, not a defiance that could change our physical situation, but one that elevates consciousness above the constraints that bind matter and energy. When physical transcendence becomes impossible, intellectual transcendence becomes the ultimate frontier. Each breakthrough in our understanding of physics, cosmology, biology, or consciousness would represent a victory of mind over the fundamental limitations imposed by our cosmic prison. The irony would be profound. In studying black holes, we would be studying the very nature of our own cosmic container. Every measurement of event horizons would be self-diagnosis of our existential condition. Every advance in gravitational physics would reveal more about the architecture of our confinement. Research into the information paradox would be investigation into our own ultimate fate, whether the information that constitutes our existence can somehow survive the eventual evaporation of our cosmic prison. Studies of Hawking radiation would explore whether some essence of our reality might eventually leak into the parent universe. But perhaps the most remarkable aspect of our situation would be the emergence of consciousness capable of understanding its own cosmic context. In a universe of unconscious matter, governed by blind physical forces, the evolution of minds that can contemplate their own existence represents something genuinely extraordinary. We would be conscious prisoners who understand their imprisonment, a condition that elevates us above mere physical matter, even as it confirms our ultimate confinement. The capacity to comprehend our cosmic situation would distinguish us fundamentally from all the unconscious matter that shares our gravitational prison. This understanding wouldn't diminish the tragedy of our confinement, but it would transform it into something approaching cosmic poetry. Conscious beings arising within a black hole interior and discovering the truth of their condition would represent one of the most remarkable developments possible in any universe, a triumph of mind over the apparent meaninglessness of physical existence. Even if we are prisoners, we would be prisoners who achieved the ultimate knowledge of their condition, and that knowledge would grant us a form of dignity and transcendence that no physical escape could provide. In the end, perhaps consciousness capable of understanding its own cosmic context is the most extraordinary phenomenon that any universe, imprisoned or free, could possibly generate. Through understanding, we transcend symbolically our cosmic prison in ways that no physical escape could ever match. Science becomes the ultimate frontier when all physical frontiers are forever sealed. When the boundaries of space-time itself confine us within an inescapable gravitational prison, the exploration of knowledge becomes our only path to transcendence. Every equation we derive, every cosmic mystery we solve, every deeper layer of reality we uncover represents a victory of mind over the fundamental limitations that bind our physical existence. Consciousness and understanding emerge as truly unique phenomena in a universe dominated by unconscious matter, following blind physical laws. In a cosmos filled with countless stars, planets, gas clouds, and black holes, all operating according to mechanical principles without awareness or purpose, thinking minds represent genuine singularities. The capacity to question our own condition elevates us above that condition in ways that matter profoundly. Even if we are imprisoned within a cosmic black hole with no possibility of physical escape, we remain unique in our ability to comprehend our imprisonment. This understanding confers deep meaning on conscious existence that no material circumstances can diminish. We don't need to escape physically to transcend conceptually the boundaries that confine us. The very formulation of this theory, the recognition that we might inhabit the interior of a cosmic black hole, represents a triumph of mind over limitation that demonstrates the extraordinary power of conscious thought. Consider the remarkable fact that minuscule humans, creatures barely 6 feet tall, living on a planet 8,000 miles in diameter, orbiting a star almost 1,000,000 miles across, have somehow deciphered secrets of cosmic structures billions of times larger than anything in their direct experience. Our physical smallness doesn't diminish the grandeur of our understanding. We are capable of comprehending realities infinitely larger than ourselves. Cosmic structures, physical processes, and mathematical relationships that operate on scales that dwarf not just individual humans, but entire planets, solar systems, and galaxies. This capacity for mental transcendence represents an extraordinary phenomenon that deserves our wonder and admiration. In an apparently indifferent cosmos governed by impersonal forces, conscious observers have emerged who question everything, including the ultimate nature of their own cosmic situation. The very fact that we can formulate the question of our cosmic nature serves as evidence of our fundamental uniqueness. No star questions why it burns, no planet wonders about its orbital mechanics, no galaxy contemplates its spiral structure. Only conscious beings like ourselves can step outside immediate experience to contemplate the ultimate framework of existence itself. Even if we are prisoners who are conscious of our state, a condition that makes us fundamentally different from all the unconscious matter that shares our cosmic confinement. The emergence of consciousness challenges any simple materialistic understanding of reality. How did mere arrangements of atoms develop the capacity to contemplate the cosmos? This question remains one of the deepest mysteries in all of science, even within the framework of black hole cosmology. The hard problem of consciousness, explaining how subjective experience arises from objective matter, persists regardless of our cosmic location. Consciousness would be a unique phenomenon operating at any scale of reality we can imagine. Even universe parents vastly larger than our own would face the same fundamental mystery. How does awareness emerge from unconscious matter? The hierarchy of nested universes doesn't resolve the ultimate origin of subjective experience. But this cosmic framework does provide an extraordinary context for our existence that transforms our understanding of what it means to be conscious in an apparently unconscious universe. We would be local manifestations of a universal tendency toward increasing complexity that operates across all scales of reality. At every level of cosmic organization, matter organizes itself into increasingly elaborate patterns. Simple hydrogen and helium condense into stars, stellar fusion forges heavier elements, planets form and develop complex chemistry. Life emerges and evolves, increasing sophistication, and eventually, consciousness arises to contemplate the process that created it. Stars, planets, life, and consciousness represent major milestones in this complexification process that appears to be universal. Our emergence would be inevitable in any universe, with physics adequate to support this progression toward greater organization and information processing. The theory of cosmic natural selection predicts an abundance of conscious observers throughout the hierarchy of nested universes. Universes capable of producing observers would be precisely those most likely to generate black holes and create the next generation of cosmic offspring. Consciousness and cosmic reproduction would be intimately linked. This means we are not alone either at the scale of our own universe or within the broader cosmic hierarchy. Countless other conscious beings would inhabit other regions of our cosmic interior, while incomprehensibly more would populate the universe, children contained within the black holes that dot our cosmic landscape. Every stellar mass black hole in our galaxy, and there are an estimated 100 million of them, could harbor conscious civilizations experiencing billions of years of history within space-time bubbles invisible to us. The supermassive black holes at the centers of galaxies, containing millions or billions of solar masses, could support vastly more complex internal universes teeming with conscious life. This realization transforms existential terror into profound cosmic admiration. Instead of being alone in an indifferent universe, we would be part of an incomprehensibly vast community of conscious beings distributed across multiple scales of reality. Our struggles, discoveries, and achievements would be paralleled by countless other minds throughout the cosmic hierarchy. The scientific quest that brought us to this understanding, from the first observations of stellar motions to the detection of gravitational waves, from Einstein's insights about spacetime to Hawking's work on black hole thermodynamics, would be repeated in countless variations by conscious beings throughout the nested cosmos. Our cosmic loneliness would be revealed as an illusion created by the limitations of our observational horizon. Beyond the boundaries we can observe, beyond the event horizons that seal off other regions of reality, conscious minds would be contemplating their own existence and gradually discovering the same truths about the nature of their cosmic confinement. Some of these minds might be more advanced than ours, having solved mysteries that still perplex us. Others might be just beginning their scientific journey, making their first tentative steps toward understanding the cosmos that contains them. Still others might have taken entirely different paths toward knowledge, developing sciences and philosophies we could never imagine. The diversity of conscious experience throughout the cosmic hierarchy would be staggering. Different physical laws in different universe generations would produce entirely different forms of matter, energy, and potentially consciousness itself. Some minds might be based on silicon chemistry, others on exotic forms of matter that don't exist in our universe. Still others on pure energy patterns in space-time itself. Yet all would share the fundamental capacity to question their existence and seek understanding of their cosmic situation. All would face the same ultimate questions. What is the nature of reality? How did consciousness arise? What is our place in the larger scheme of existence? And perhaps most importantly, What meaning can we create within whatever constraints define our existence? The answers to these questions might vary dramatically across different scales and forms of consciousness, but the questions themselves would be universal. The search for meaning, purpose, and understanding would unite conscious beings across all scales of the nested cosmic hierarchy. This final conclusion transforms what could be existential terror, the realization that we are prisoners in a cosmic structure, into profound cosmic admiration for the extraordinary phenomenon of consciousness itself and its capacity to transcend any limitations through the power of understanding. If you're still awake, it's because the content was really good. So take a moment, leave a like and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.